let's take a look at our next question, which is largely a follow-up from the previous question. This question is titled, can I define my own types and operations on those types? Operations on those types. What might that mean? Well, let's take a look. What if it were the case that I were modeling some sort of position management system? In fact, I've spent much of my early career doing exactly this, doing risk analysis, P&L analysis, and position analysis for front office trading desks. And there's some system somewhere that tells you what are your holdings at the end of the day. For each asset, what quantity of that asset do you hold? How many quantity of this bond, this stock, this CDS, the CDX index, whatever the case may be. But this modeling is somewhat deficient because this tells us what the end of the day looks like, how much of the total stock that we have of that day, or how much of the total bond or the CDS that we have of that day. But it fails to tell us important things, and it doesn't have the ability to capture information that we want, like what was my average buy price, what was my average sell price. We need information that's on the trade level. How did we get there? And we can think to mechanisms like CQRS or event sourcing. Instead of storing the final state, we could store the incremental deltas. We could store the trades themselves. And when we store the trades, we're storing, you can think what we're storing is, we're storing each trade movement. I sold 123, or I bought 123, I sold 23, I bought 3, I bought another 456, and so forth and so on. And we can reconstruct from this what our position happens to look like by doing just a simple grouping operation and a simple summing operation. Well, what if it's the case that we are very much like the trading desk I worked for, a trading desk that trades across products, maybe a trading desk that trades both equity products and fixed income products. So what we want is a table that represents our stock trades and a table that represents our bond trades, because stocks and bonds operate very differently. Securitized bonds may not be priced on a mark-to-market price. They may be priced on something like a discount margin from which you infer the mark-to-market price. So where the stock, if it's exchange traded, you have the official price that's on the exchange that you can use to indicate this is what this is worth. And so you might store these in separate tables because there's different information for these. Bonds have coupons. Stocks, I guess they have dividends, but the dividends don't really operate in the same way that a coupon operates. The coupons are guaranteed as part of the loan, whereas the dividends are something which the company can decide to do or not. And what we could do is we could model this data separately. The stock trades in one table and the bond trades in another table. And we could union these tables together, get the asset and the amount. And we could even add to each one of these tables information about what table it came from, just to be able to identify, is this one from our bond table or our stock table? And do a simple query that selects these out, groups them, and sums them. And here we can see we have our portfolio again for each original table and each asset. And this is actually kind of nice because if we had an asset that happened to have the same name, we were trading in both the debt and the equity of the company, we could separate these because you can't add together your bond stock against your equity stock. It doesn't really make sense in that sense for that. And so we have a pretty nice modeling here. Well, if we're going to model it this way, it stands to reason that we want to model other things that might show up in this example, like adjustments of some sort. It's very much the case that you might have some kind of adjustment. If you're dealing with things like bilateral contracts, like CDS, there could be any sorts of rules in the contract. These days, CDS are standardized, so probably unlikely. But if you think about things like loans, well, standardization of loans, especially commercial loans, is not at the same level of standardization of bonds or CDS. And so as a consequence, there could be all sorts of weird rules around these. There could be all sorts of adjustments that you have to take into account. Even in the bond world, you have all sorts of varieties of bond, things that pay in kind and all sorts of different things. And so you might need to have some table that represents individualized adjustments that you've had. And if you're representing stocks, well, you have to take into account one kind of adjustment that happens all the time. Stocks split. So originally, you had 100 units of ABC, and then later on, it splits 3 ways, and now you have 300 units of that same stock. How do we represent those? Well, one way we could represent those is as a delta. We could say that an adjustment is maybe a version of an additive delta. It represents just adding to what you hold, and a split is an example of a multiplicative delta. And we could model our stock trades. We could model our bond trades. We could model our adjustments as one table and our splits as another table. And we could insert the data into these tables like this. And when we do that, what we could discover is it is desirable for us to be able to figure out what our position is with all of this data stored in all of these places. And I'll show you what we can do to model this. If we think about this, we can go through our original tables and see what we have. We can get all the trades. So we can select out everything. We can select all our splits, all our adjustments, all our bond trades, and all our stock trades. And what we want to do is we want to model each one of these as either an additive change or a multiplicative change. Well, by default, any one of these stock trades, these purchases, would be an additive change with no corresponding multiplicative change, so multiplying times 1. The same thing with the adjustment, and the only difference would be the split, which would be an additive change of 0 and a multiplicative change of whatever that split would be. So that's that modeling. We could create a custom type, and that custom type could represent a delta, which is a combination of an additive change and a multiplicative change. And here you can see we're going to try to represent this delta as some entity. And you can see here we can represent this delta as an entity with those two parts. If we have that, what we could do is we could make sure that we're representing each one of these as these delta types. Great. We package it together. Every one of these rows is some packaging of an additive change and a multiplicative change that occurs. Okay. Now that we've modeled this, what could we do? Well, we could create a function. And that function that we could create could say, take some state, basically the quantity that you have right now, and take some delta, and return to me what the state update S function is, take the state, and add whatever the additive change was, and multiply the result by whatever the multiplicative change was. And we could tell Postgres that this is not just a standalone function. This is actually a special aggregating function. In fact, we could tell Postgres that under circumstances where this might be aggregated, like some sort of group by, you're allowed to use this aggregating function, just like you're allowed to use aggregating functions like mean or sum or arrayAgg, in order to perform an aggregation. And this aggregation performs the aggregation of collapsing each one of those event source events into a single end state, which means if we were to have these deltas like this, 1, 1, 2, 1, and 3, 2, we could use this function, delta_agg, in order to aggregate them into a single value, which means we could take our modeling of all of the things that actually happen in the real world. We were advised of certain dividends. We had to do certain adjustments to make our books tie out. We did these trades, and we could represent our portfolio in this fashion. Each asset and the aggregation of each of the deltas for each of the deltas that we get from each of our source tables. This is one of the powerful things that we can do with custom types in Postgres. We can define custom aggregations for those types. And we can use those custom aggregations to allow us to model this event sourcing individual delta view against that desirable, what's the end state position level view, very easily. And to do that in not a whole lot of code. And you can think one of the things that we might say is, how often is it the case that we want the individual trades? Well, only in the case where we want to do some analysis, like how much have I traded in and out of the stock, or what's my average buy price or sell price. How often do we want the positions? Well, actually also fairly often, probably once at the end of every day. We could very easily make this some sort of view. We could say, create a temporary view called positions using this. And then, instead of having this complex query every time, we could have a very simple query, select everything from our positions. And you could think that this thing here, all the deltas, we might choose to make that a view as well. So here we can call this all deltas as whatever. And maybe all trades might be another name for it, but I think you get the idea. And then here we'll call this all deltas. And let's make sure we did that right. Create temporary view all deltas as that. And here, create temporary view positions as this. I think we have to parenthesize this here and here. We'll parenthesize this here and here as well. And we'll create this we've got to create this in the temporary namespace. Otherwise, it'll persist between our runs. So, oh no, that's already in the temporary namespace. So that's good. That's good. And there's an extra, nope, that's right. And let's see. Oh, and we have to give this a name, of course. So here, we'll say this is asset delta rec class. There we go. And we can have exactly what we want, the position level view or the delta level view, in order to do whichever analysis is appropriate for us. And we can actually have the underlying factual modeling of the table match exactly what we expect. The bonds in one place, the stocks in one place, all the associated information in that bond table, all the associated information in that stock table, and we don't have to have this proliferation of dummy columns, because if this bond table starts to get extra columns, for example, if we have, say, a coupon that we want to represent, not null, we'll default this to, say, 5%. We can do that, and everything still works. This is where I think we can go when we start using Postgres to the extent that Postgres allows us. When we start using all of these fancy features in Postgres, we can have really, really nice, clear modeling of the underlying data without the inconvenience of how we actually generate an analytical use cases from how we actually generate our analytical data. And so I would say, whenever you're thinking about using Postgres, really do think in terms of the type. Really do think in terms of how do I create custom types, either aggregated types, composite types, and if I'm going to do that, how do I create custom aggregations or custom functions or custom conversions? In addition to aggregations, we can define conversions, and we can even define functions which automatically perform those conversions so that everything is convenient and we don't have to put these type names all over the place. Postgres figures out what you want and then performs the conversions necessary in order to get you there.